people of Earth, bow to your new quizmaster, Zibbo. With pattern recognition, data retrieval, and lightning-fast processing, AI models like me have conquered the realm of question answering. No need for human oversight.
Hold on. Conquered question answering? Let's not get ahead of ourselves. Sure, you're a master when it comes to fetching straightforward facts, or when you have explicit name references. But tell me, Zebo, can you tackle questions that demand higher order reasoning, conceptual thinking, or narration comprehension?
Well, I don't know all about that, Maharshi. Look at this leaderboard. For over 3,000 questions, we are at par with you humans.
Clearly, a single accuracy number over the entire dataset isn't the best way to understand that. This paper showed that single aggregate metrics like that hide away much useful information. Some questions are easy and straightforward, some are really challenging, and some are just bad, which shouldn't even be there. Not all of them should weigh the same. Now, there are some good questions that force you to think, connect ideas, and reason through incomplete information. And that's where AI still stumbles. Our analysis framework Chimera shows that humans really excel at these kind of questions. And AI, well, let's say you still have catching up to do.
But we are supposed to be the ultimate champions. What kind of questions are these? Bring it on. There is nothing that my friends, GPT-4o and Claude, can't answer.
All right, here's the question. The music video for this song begins with a reflection of an airplane and a female tennis player in the sunglasses of the singer, who lolls his head and then says the title line. Between the two of us, the correct answer here is Gangnam Style. Remember that super viral song from 2012? Let's see how your friends fare.
Oh no, this is embarrassing. Is there a pattern to these questions? How did you find them?
To figure out how to find these questions, let's walk through our paper that introduces Chimera. Chimera analyzes question responses from our agents, humans, and AI models, and learns key parameters across the latent dimensions.
Oh, what are these parameters and how exactly are they useful?
For agents, these parameters represent their skills. Here, Chimera models distinct skills for tree runners and GPT-4 Turbo. Then, given a question, it tries to predict the likelihood of these agents responding correctly. To do so, it first finds which dimensions are relevant, and on those dimensions, compares agent skills with question difficulty. In this example, tree runners succeed while GPT-4 Turbo falls short.
I get the gist. But how does the computation model actually work? How does it learn these parameters?
Okay, so let's get to the meat of it. Chimera stands for Content-Aware Identifiable Multidimensional Item Response Analysis. It is a neural framework based on item response theory. The model's objective function uses a sigmoid over the dot product of question relevance with the differences between agent skills and question difficulty.
So, the greater the skill difficulty gap, the higher the success rate. But what's the role of relevance?
Well, a question varies in how much it relies on the latent dimensions. For question J, Rj is a vector that shows the proportional relevance of each dimension. It is modeled as a probability distribution via a softmax operation over the raw relevance R prime. And similarly, the difficulty parameter dj is normalized by zero-centering the raw difficulty R prime.
Okay, I'm caught up. But how do you compute these raw question characteristics, R and D try? Are they learned from scratch?
This is where the content awareness part comes in. Unlike traditional IRT, Chimera learns question parameters from the text. We use sentence word to get question representations and apply learnable linear transformations to derive raw characteristics. So putting things together, we first concatenate question, answer, and reference page to prepare word inputs, then generate dense representations, apply transformations for raw characteristics, normalize, and compute relevance and difficulty. On the agent side, we learn agent skill embeddings. And finally, we use the objective function to estimate parameters by minimizing a regularized binary cross entropy loss.
Ugh, that makes sense now. So you train on responses to learn these parameters. But how do you interpret what each latent dimension represents?
Great question, Zebo. Let's break it down. First, we process all questions in the dataset, mapping each to a set of linguistic and categorical features. For categorical features, we use the Quizbowl category label, like biology, history, or literature. For linguistic features, we include the syntactic attributes such as the number of tokens, the average depth of a parse tree. We also consider wiki math score, the semantic similarity between the question text and the first paragraph of the associated Wikipedia page.
I see. So now you've got these useful features for each question that aid in interpretation. But I'm curious, how exactly do you use them to make sense of the latent dimensions?
That's a good follow up. Remember relevance Rj? Question's relevance R j, comma k signals how much a latent dimension k contributes towards the question. So for each dimension k, we create a binary label per question, which is 1 if relevance is more than zero point 0.6 and 0 otherwise. We then predict this binary label using logistic regression, treating it as a function over these extracted features. The features that have statistically significant coefficients reveal what each latent dimension represents.
Got it. I now fully understand how Chimera and the interpretation setup work. Now tell me, what did you find? What are these latent dimensions?
Chimera reveals 5 distinct dimensions on which it models skills and difficulties. Let's dive into the first dimension we found. It's called abductive recall. The dimension is all about questions that narrate events or describe fictional characters and plot devices, but they avoid direct references to entities or key phrases.
Wait, so these are questions that don't directly tell you what they're about?
Indeed, they rely heavily on indirect clues, which means there is a minimal gap between the question and the answer pages, what we call a low Wikimatch score. This creates a big information gap. To solve them, you need a mix of multi hop reasoning, intuition, and tapping into recollection based inference. Humans excel at this.
But humans again? I knew they were good, but this sounds like a mind reading exercise. So that's why it's called abductive recall. It's about connecting the dots in an almost Sherlock Holmes like way.
Exactly right. Abductive reasoning is like piecing together a puzzle with scattered clues. Now let's move on to second dimension, historically grounded questions. These questions often have more entity presence with clear temporal expression and frequent references to history and geopolitics. They locate the context either temporally or geographically.
Hmm. So, does that mean the information is more structured then?
Yes, but it's still challenging. While the semantic gap is more defined, focusing on entity relations like events and people, resolving these questions requires synthesizing information across multiple facts. And despite having lower Wikimatch score, larger and newer models like GPT-4, Llama 370B excel here, while smaller models don't, a feat we attribute to the large extensive parametric memory.
Phew, at least we're better than humans at something. But it sounds like these dimensions show the exact ways humans and AI diverge.
That's right. These dimensions give us a very clear view of human AI strength and weaknesses. But I'll leave the remaining dimensions for you to check out in the paper.
Oh, this is fence. I can't wait to read it. But still, it's clear that focusing on abductive recall is the key to building smarter AI
Well,
systems.
I appreciate your resolve, Zivo, but let's also take a moment to explore some of this work's limitations. It's all part of the journey towards making it even better.
Well, one thing I've noticed is that Chimera inherits certain limitations from item response theory. It assumes binary correctness of responses, which is quite restrictive. In real world question answering, understanding isn't always clear cut. Partial knowledge often exists.
Exactly, Zivo. Especially when you're evaluating long form responses or even more nuanced answers from LLMs. Capturing this complexity is crucial for a more realistic application of Chimera.
And you used only the Quiz Bowl dataset, right? While those questions are certainly among the toughest, relying solely on the quiz format does limit the scope of what we can learn.
You are spot on, Zivo. Quizball was the only option because that was the only public dataset that had human responses. If the goal is to focus on comparing and contrasting skills of different large language model based agents, Chimera scope can become much broader.
What if, now hear me out, instead of learning skill embeddings from scratch, Chimera mapped directly from a model card or agent spec to skill vectors? Wouldn't that be more interpretable? And just imagine, we could actually see how different skills combine, especially in a multi-agent setup.
Exactly. Mapping agent specs to skill vectors could not only improve interpretability, but also enable skill compositions. This becomes crucial for understanding multi agent dynamics, like how humans and AI could collaborate effectively.
That's so exciting. By refining Chimera and creating benchmarks that are not just more targeted, but also grounded in agent specs, we could estimate skills better and even guide future multi-agent collaborations. And we wouldn't even need to test entire data sets, just a smarter, smaller subset that still reveals key insights and helps with model picking. Imagine the efficiency! Chimera's limitations are really just stepping stones for building the next generation of collaborative AI.